All right, well, let's get started here. Kit had some life stuff going on, so he'll be joining us in a few minutes, but we will carry on without him. So let me start by sharing my screen here. I will try to do my usual thing. I'll make this a little bit bigger. Please post in the Discord if you have any trouble seeing, but I think this should be a good size. I don't, like I said, at least right now I'm my partner in crime, so I'll have to bounce back a little bit in just checking out the Discord. So actually, I think I've got an iPad next to me, so maybe I can have some dual screen action going on here, so I can see what folks are saying. Let's see. All right, awesome. Okay, so where we left off last time was we were doing some fun debugging of we didn't have things quite working at the very end with the feature we were working on where we wanted to essentially catch arbitrary user-defined errors that occurred. So here we had the ZIO.succeed, and ZIO.succeed is supposed to just like take code that's just gonna return some value, right? If we go to the signature of succeed, it is just supposed to return with the value. It's not supposed to fail. In one sec, let me just, I think someone's having trouble joining. So let me just grab the Zoom link here, see if I can send it. Oops. Well, hopefully that works. Okay, so this is not supposed to throw any exceptions. Something's just supposed to return this A. But one of the things we know is when you give people the ability to put arbitrary code somewhere, they're going to use it either intentionally or unintentionally to do all sorts of crazy things. And so we wanted to handle this possibility that you had this succeed block, but maybe an exception got thrown there. And that was the idea of these die failures in ZIO, that because the ZIO succeed says that it doesn't fail here, we can't fail with the typed error, but the fact is you could still throw an exception anywhere. So we want some way to handle that. And we were modeling that as part of this die cause. So we had failure, we had die, and we had interruption. But we needed to update our logic in the run loop for this. And so we basically just had a little bug here where what we were doing before is in the implementation of this succeed node, we were first popping the next continuation off of the stack, doing the stack.pop, and then we were evaluating this thunk. And that was actually the wrong order because if we do that, then we kind of get left in a little bit of an inconsistent state because we popped something that we shouldn't have popped. That is like the next continuation, is potentially the next error handler. And so this is one way this is what we call like a stack corruption issue of when we do this like low level implementation here and we have this run loop, we're maintaining this explicit stack. The stack is basically the call stack and it's dynamically typed. If we look at this, it's just this stack of these continuations that are just basically functions from any to ZIOs of any. And so we take on the responsibility of making sure that those continuations are well typed. And if we have one that's int to string and we have the next one that's string to double, the next one that's double the list of ints, that each of those are in the right place in the stack, that we run one after the other. And by popping before we did this evaluation, we were getting those out of order. We were kind of dropping one that we shouldn't have been. So that's why we had those issues at the end of our last session. So the solution that I just posted after our last session was we basically just want to do that evaluation before we take anything from the stack. And then if we run this program, we get this line being printed here. So here we said we were going to succeed with just some value, right, with a number 42, but an exception got thrown here. And so this got translated to that die channel because that was an unexpected failure. And we use this catch-all cause operator, which is the more powerful error handling operator that lets us see the full cause of the failure. And we use this little debug thing to print that out. And what we got was one of these die causes with the runtime exception inside of it. Any questions on that before we go on here? All right, cool. So our goal for the day is going to be working on implementing interruption. And so what we can already kind of do today is if I go to my little ZIO trait here, or my companion object, I should say, I can already implement another constructor here. So let me call this interrupt. And this can actually be a val right now, at least. And this is going to be a ZIO, nothing, nothing. And I'm just going to fail with this cause.interrupt thing. Calculation here. And so with this, what I can do is I could create a new program. So let me call this, I'm going to call this self-interruption example. And what I'm going to do here is I'm just going to do ZIO.interrupt. And we'll start by actually just doing this. And I won't run this, but now I'll run this guy. Actually, I do want this. So let me run this. And let's see. Okay, so this is interesting. All right, so this is getting us to another little update we have here. Oh, okay, so this is giving us an exit. So let's do this. Let's do val exit is equal to this. And then let's print line the exit. Okay, and so you see when we run this program, we just get a program that fails with this interruption cause. And so this self-interruption is kind of you saying like, hey, I'm going on with this computation, and somewhere as you get with the computation, you get to a point where you decide it no longer makes sense to continue. And so that's why it's called self-interruption, because you're the one who's deciding, hey, based on what I'm seeing, I know that I shouldn't continue. And so this actually is used in a couple places in ZIO itself. Let me see if maybe I can click through to a link for you here. Let's see, do we have a queue somewhere? So maybe this clicking through may not work for me. Yeah, okay, all right, that's not gonna work for me. Okay, anyway, a good example of self-interruption is if you're using the real version of ZIO and you offer a value to a queue, or you try to take a value from the queue and the queue has already been shut down, the implementation is just going to return this ZIO.interrupt here. It's basically going to say, hey, I was doing this work of interacting with this queue, and the queue I see now has been shut down. I know that is a signal for myself of I should stop doing further work. So I am just going to return a ZIO.interrupt here. And we can see this is pretty straightforward. This essentially already works today with the existing machinery that we've got here of having introduced this cause thing. But what we'd really like to be able to support is what's called external interruption. And so external interruption means rather than me saying, well, I need to stop what I'm doing for some reason, someone else coming up to me and saying, you know, Adam, you were doing all this working on this PR, stop your work on the PR, you need to be done. And so for that, what we're going to want to implement is we're going to want to go to our fiber tray here. And so right now we just had this one method on this fiber that basically waits for the fiber's result, that joins the fiber and says its result now becomes our result. For this, we're going to want to implement at least one other operator, and we're going to end up actually implementing a couple of them. But to start off with, let's say we'll have this one called interrupt. And so this is going to give someone else who's not us the ability to say, we don't need to continue doing the work that we're doing. And this is a really useful thing because a lot of times in a larger system, an individual fiber is just doing its local work, right? Like you forked it off and you told it, hey, go and load this file and process all this data from this file and transform it and write it to this other place. And all that fiber is concerned about is the writing and the processing, and it doesn't know anything else about what's globally happening in the rest of your program. But now maybe you have some other part of your program that knows something else, right? Knows that the person who just requested this data just like closed the browser, or knows that something else happened. Maybe knows that we just got a cached version of this data from somewhere else, and that we don't need to do this anymore. And so this interrupt operator is going to give us the ability to externally say that we don't need to do this anymore. And as part of this, we're actually, I think, going to want to implement a couple of other operators on here. So one of them is we're going to want to have an operator called interrupt fork. And the difference between interrupt and interrupt fork is whether we're going to wait for the interruption to complete before this returns. So interrupt is going to say, I want to send a message to this fiber to stop what it's doing. And then interrupt is not going to return until the fiber actually has stopped doing whatever it's doing and has wound down with whatever its wind down logic is. Because at least as we build on more on this, as we go farther, one of the things we're going to want is the ability for the fiber to do some logic once it gets the interrupt signal. You can think of the interrupt signal as saying, I want you to stop, and at that point the fiber needs to stop, but it also may need to do some wind down. It may need to like close a file, handle it's working with, and we want it to be able to finish doing that stuff. So first we're just going to implement interruption itself, but eventually we're going to want to implement that idea of wind down. And so this is going to wait for interruption to be processed. And then this interrupt fork is going to do the opposite. This is going to send the interrupt signal to the fiber and then return immediately. So if you think about like this actor analogy, this would, I think at least I don't think they really support this anymore, but like there was that idea of like tell versus ask, right? Of like tell was kind of fire and forget, of like send this message and you just move on with your life. You just know it's in the mailbox somewhere, it'll be processed eventually. That's what interrupt fork is. Interrupt is a little bit more like that old like ask pattern of like send the interrupt message, but then actually wait for them to send you back an acknowledgement of I have received the interrupt message and I have processed it and I am done with doing that. So that's the difference between those two. And then we're actually going to want to add one more here that's called await. And so the difference between await and join is await is just going to return the result of the fiber, but it's not going to make it quote unquote our result. So even if the fiber failed that we're awaiting, we'll see that failure and we'll be able to do something with it if we want to. We can print it or we can do some different logic based on it, but we're not going to fail ourselves based on that. And so what we're going to do here then is that's going to help us simplify some of this logic because, let me see if we already have this operator. Yeah, we do. So we've got this done operator that just takes one of these exits and just puts it back into a ZIO. And all it does is just matches on it. And if it was a success, it puts it back into a successful ZIO. If it's a failure, it puts it back into a failed ZIO. And so what I'm going to do here is I can now actually implement join as just await flat map ZIO.done. And I can actually make this final, and I think I'm gonna have to go back to some of my fiber logic here because I'm gonna have to change this. So let me just make a note. I'm gonna come back to this in one sec, but I'm gonna first finish sketching out the interface. I'm back to compiling at least. And now let's go back to my fiber. All right, so we've now got await as a primitive. We saw join, we could just implement in terms of await. The other thing we can do along similar lines is I can actually implement interrupt in terms of interrupt fork and await. And I'm going to make a change that we have in ZIO as well, that when you interrupt something, you probably don't actually use this ability much yourself, but when you interrupt, because you've waited for its result, you actually get the exit value and you can look at that. And so once you interrupt something, you can see either it got interrupted, or maybe by the time you sent it the interrupt signal, it had already finished and it finished successfully. So if you want to, you can look at the result of the fiber once you've interrupted that way. Oh, and I don't have the little zip right implemented, so let me do that. So let's see, I've got let me just do this from here. And then what's these? So then we don't need to implement interrupt here. Okay. And so now we've basically got two primitive methods on fibers. We've got this await and this interrupt fork. And let me just clean this up slightly. And then we've got these two methods that we can kind of derive from that. And so now, if I can just implement these two methods, and this one should be pretty straightforward. I think I just need to take my previous logic for join and just adapt the type signature a little bit to fit this. And then I can implement interrupt fork, then I can actually have all of this stuff, and I can have kind of pretty close to the full like ZIO functionality of like what you could do typically with a fiber. All right, let me just check in for a second on any questions people have. Oh, I think, let's see. Oh, Kit is ready. Okay, hold on one sec. Let me switch over. And also, yes, hold on one sec. Participants, boom. Promote. Okay, and let me also do a little share here.
Yay!
Yay! All right, and 1 second. I'm just going to give this link to Kit.
Thank you very, very much. Sorry for the disruption.
No, you're fantastic. Okay, and I've answered this live. Okay, awesome. So I think we're good here. All right, so first let me try to adapt my signature of join to be the one for await so that we can at least recover our existing functionality, and then we will continue here. So previously for join, I was doing this. So I was using this ZIO.async, and then I was saying once I had the exit, just call back with ZIO.done exit. And remember, ZIO.done takes an exit and turns it into a ZIO. But here, I think I just want to return the exit. So I think I just need, let's see if that will work for me. Yeah, I think I just need a little bit of type foo there. Well, you know, I don't think I even qualify as that. But I think that should get things working there. So let's just try running one of our examples again. And maybe let's try, I think we had some examples that were like slightly more real with parallelism. So I think we have this my parallel workflow. So let me get my parallel workflow running. I won't run these guys. All right, so let's make sure that our existing fiber-based functionality actually works here. Okay, perfect. So this, even though it looks pretty like high level under the hood, is forking two different fibers and then is joining them. And you can see that because this completed in 5 seconds versus this should be 3, 5 was running sequentially, would take 8 seconds. So great. So our existing functionality is working and we've kind of got the building blocks now to go on and interrupt and implement this thing. And so the only actual like to be implemented thing at this point is this interrupt fork. And we said above that the semantics of this was that this was kind of the fire and forget version. If we go back here, we said that this was going to send the interrupt signal to fiber and it was going to return immediately. It was not going to worry about getting anything. It was just going to send the interrupt signal. And so it's going to be like the tell method on an actor if we're kind of used to the bang symbol and all that fun stuff. And so how do we go about implementing this? And so what we're going to do is we've said before that whenever the external world interacts with a fiber, the way they're going to do it is through this nano actor interface, through sending the fiber a message. And we even created this little fiber message tree. And right now, the fiber message has 3 different messages that it can have. It can have start the fiber, add someone who's interested in the final result of the fiber, or this one we use internally where in the implementation of async of call the fiber back when you've got some result for the fiber to continue processing. And so if we want to support interruption, we're basically going to add one more case to this protocol, you could say. And so I'm just going to do case object interrupt extend fiber message. And now, because Scala is nice, I'm going to get a new message here that I need to actually handle this possibility. So I'll say case fiber message dot interrupt. And right now I'll give myself a question mark here. And now I've actually got everything I need to implement that interrupt fork operator, because all this is offer to inbox fiber message.interrupt. And then because this is a ZIO, I can just wrap this in a ZIO constructor. And so that's kind of everything here. All you do externally to interrupt a fiber is you send it this interrupt message. And then if we go back to the actual interrupt method here, this one that gives you the X as well, you send it the interrupt message and you wait for its result, which actually seems pretty intuitive. One thing to note here, by the way, is I think at least over the last week or so, there's been a lot of debate about Twitter about at least for some people, about whether you should like back pressure on like interruption. And I think back pressure is like a terrible word for it because you're not back pressuring, you're just waiting for something to be done. But I think the way I would suggest you think about this is basically sometimes you want to do both. Sometimes you want to fire and forget and just say like, hey, I want to tell this thing to stop and then I want to move on with my life. And sometimes you want to tell this thing to stop and know that it has stopped and then move on with your life. Both of those are important semantics, and at least with ZIO, it's very easy to use both of these. In ZIO 2.0, actually this interrupt fork is the most primitive one, and then this interrupt is built on top of this, but it's important to be able to do both of those things, both this most basic level of fibers as well as at higher levels. And in ZIO, there's an operator called disconnect that lets you take any effect and return a new version where when you do interrupt it, the interruption will proceed in the background and you'll be able to move on. And so you can really have both semantics depending on what you want to do with them.
And just to sort of like, because I don't think we've added the complexity that would like, oh, what's the difference between waiting half a second for it to be interrupted or not? But eventually, as we continue along, we're going to have uninterruptible regions. So then interrupt will have to wait for those uninterruptible regions to finish, right? So if we want to like release a resource, this might take, you know, a long time if that uninterruptible resource deallocation takes, you know, 5 seconds. So that's just, we'll build that, but yeah, that's great.
Exactly.
I missed the
okay.
wars on that one. I gotta pay more attention to Twitter. There's always something there.
No, I'm not sure you were missing much. Okay, so we have the implementation of sending the interrupt signal. We still have to do this implementation of processing the interrupt signal. And so I think this is one where we'll start with like a very basic implementation of this. And I think as you were just alluding to, there's like more complexities we can build on. And I think we'll kind of build them one at a time, but we'll start with something that is kind of a very minimal thing, and then we'll kind of build up from there. So I think the most basic thing we could do here is we could just here. So basically, and so sorry, let me actually even step back a little bit and just remind us where we are in processing this. So this process fiber message is when the fiber internally is taking from that inbox. And so we're proceeding sequentially with everything. When we're processing this, nothing else is happening on the fiber because this is what the fiber is doing. And so that's going to make our logic kind of easy here. And so I think a way we can approach this is there are kind of two, I think, initial possibilities of whether the result is null or not. And so if the result is null, then this means fiber is still running. And if the result is not null, then this means the fiber is already done by the time we have gotten interrupted. So if the fiber is already done here, then at least in our kind of simple version here, there's really nothing that we need to do here. And in fact, this just can return the unit value, so we can kind of just return unit, or I mean, if I'm simplifying, I can just delete this branch of logic, but maybe I'll just kind of leave it here just so to kind of reflect that we consider this possibility, and that's what we're doing with it for now. The second situation is the fiber is not done yet. And so again, we'll kind of start with the simplest situation, but at this point, we don't have any concept of like, you can be uninterruptible or not. So at this point, we put the knife in your back and you're going down. So we can say result equals exit.failure, cause.interrupt. And then an easy thing we can do here, well, maybe I'll just copy this below this note, is we can just say, well, we can kind of do two things. We can either, that's probably actually a fine thing to do, or we can kind of continue running the run loop and, yeah, actually, let me do that one. Let me just show us that one, because I think that'll be a little bit more what we're going to do. So if we're not done yet, then we'll set the current ZIO to being ZIO.failCause. I guess I can just use actually the nice little constructor I made a minute ago, ZIO.interrupt. And then I can call the run loop again. So let's see if that will work for us. So let me create val interruption example 1. And so let me, and actually to motivate this, maybe let me implement something that we don't have yet. So if you've worked with ZIO, you may have seen an operator called ZIO.never. which sounds like it wouldn't be very useful, but actually it can be relatively useful for a bunch of things. But it's basically a ZIO computation that never completes. And so just like ZIO.unit is just a value that completes with this value that has no information. These things seem simple, but sometimes they can be useful when you kind of put them together with other things. Right, of like ZIO.never is a nice way to just wait forever. Like maybe you fork something off to do something in the background and you just want to let the server run forever. And so you just do ZIO.never after that. And you might have wondered, well, how is never implemented? And so this is ZIO that never fails and never succeeds. And a really simple way to implement it is just this ZIO.async thing that never calls the callback. And so this isn't going to use any resources, it's just going to never return. And so let me maybe use that as a little example here. So like first thing I'm just going to do is I'm just going to do this ZIO.never. And I'll do interruption example 1 dot unsync.
And I've added us a read line so we can do the usual user triggered.
Oh, sorry, I'm running the wrong one. Let me, oops. Let me uncount that. All right, so let's run this one. And so you can see this is just suspending forever. Eventually kind of kill that thing. So great. So okay, we can run something that never completes. High performance programming here. But now let's try to do something a little more exciting. So let's fork this thing off into a fiber. And then maybe I think we already have some version of sleep. Let's see.
Want to do the read line?
Sure.
You gave us one so we could like do it ourselves.
Okay, great. All right. So then we're going to read a line. And once we're done reading the line, we're going to interrupt this fiber. And we will see, just like we did before, whether the stuff we've done works, and it may or may not, and we'll have fun either way. Let's see, does this print something?
It should be printing a little arrow, but maybe that didn't quite work. Let's see.
Let me try again. Maybe I haven't saved.
Do we have no? Yeah.
Okay, so maybe we're not hitting that. Let's do a little bit of debugging. We have a little debug thing, right? We have debug.
We have debug. Yeah, it's just debug.
Starting. Yeah. All right, let's.
Oh.
Okay, so we did fork. Oh, I think this might be. I think depending on whether you're in a forked like SBT thing or not, you can have some weird issues with
read line. Oh, so okay. Well, let's never mind the read. Let's just sleep then.
No. So yeah. So I think we have some speak with delay or something. So let's try using that. So speak with delay. All right. So we're going to wait 3 seconds and we're going to interrupt it.
Mm-hmm.
Let's try this. We started it. We forked it. We're waiting. Okay. And now, all right. So we have not interrupted it. So this is a good little. Okay, so let's see what we've got going on here. So let's create a little debug message for ourselves here. Let's see, process fiber message. Let's just start.
Maybe also you print the results in case. I mean, there shouldn't be one at this point. Yeah, I don't know.
We can also go back to just a very simple way of doing it and build up from there. But let's make sure this is okay. So it has received the interrupt signal. Okay, that's good. So then. Okay, so the fiber's still running. So we set current ZIO to ZIO.interrupt. Then we go to the run loop.
Should we see if we got down to ZIO.fail, right? That's what ZIO interrupt is going to do for us.
That should give us a fail cause here.
Okay. Whoa. Oh.
Okay. All right. So we're saying we got
die. Very intense.
Then why are we getting a no such element exception? So we've got some other. Yeah. So okay. So we had a cause.interrupt. So we find. Oh, you added this later. So we
I did add that later. So I'm not sure if we find a continuation print line continuation. You want to run that again?
Yeah, sure.
What do we find? This is more debugging than our usual topic. Definitely the details. Okay. Uh-oh, might want to kill that early.
I did, yeah.
Okay, we still have.
Let's see, was this the first one or second one?
Oh, that's a good point. This might be. Oh,
all right, let me
hit the little trash can maybe first. Oh, there we go.
Yeah. All right, sorry, folks.
Have your trigger on that kill button. Oh yeah, because you got to run project. Yeah. Oh yeah, I saw some stuff in the middle.
Yeah, so let's see what we got here. So we received the interrupt signal. It was null. The fiber's still running. Set the cause equal to cause.interrupt.
And then we
found a next error handler, which is interesting. Did we, or do we have a bug here?
Because it seems like we're never printing out either case after fiber is still running, because I have 2 print messages that should occur next after that. So loop true, continuation.
No. So this can return no. Let's look at this. And then when we call this,
it's odd because I never saw anything getting printed after cause equals interrupt, right? We don't see that. We don't see found, or we don't see no continuation, and we don't see a continuation.
I feel like we are still looping in here.
Yeah. Could pop be throwing an error if it's empty instead of returning null? Oh, yeah. So we probably just want to do a try around that. That makes sense. So yeah, I think.
That's okay. All right. So yeah, maybe that was maybe stupid. Well, so we.
Oh, then we're catching this error at the top, and then
exactly. So
die.
Yeah, well, or I think we just check whether it's empty, right? Instead of this, we could just say if stack is empty.
Yep. Else we could do stack dots. Wow. Yeah, that works.
And then exactly, get rid of that.
Yay.
So know whether your data types return.
Yeah, I guess it's the one danger of that we have this whole big try catch around our entire run loop is if we actually have an error that's not sort of the intended to catch a user defect, we're going to be catching our own defects, and it's going to make it very difficult to tell.
Okay, so there we go. So now this thing returns. And yeah, so let's maybe take out some of our debugging statements just to make this a little bit nicer. Yep, let's see if we have any other.
I think I got the rest.
Okay, great. Okay, perfect. So yeah, let's try running that one more time. Yay for saying let's figure things out. Okay, great. Okay. So yeah, so let's look at it. So we started, we forked, we said hello. So I think the only thing that's a little bit weird here is if I do val exit equals this, and I do, let me just make sure this null is coming from where I think it is.
Oh no, there was one last debug.
Oh, okay. All right. Let me just run this and let's make sure this is actually giving us our interrupted exception.
For sure.
Okay, so that's not quite right. So let's
wait, actually, is it though? Because we interrupted the fiber, but
yes, you're totally right. So I guess okay, that's a great opportunity for us to show some of these semantics. So let's say we interrupt it and then we join it. Now this should fail with an interrupted exception.
Sure.
And let's see if it does.
Yeah.
Okay, great. Okay, so good. So this is like the most basic interruption here. And so you can see it's got kind of two parts. It's got how we send the interrupt signal, which was in this interrupt fork. And this is actually super simple. And this essentially will stay exactly this simple through like everything we do. And then we have the second part of it in this process fiber message of how we handle the interruption. And that's the part that is going to get more complex over time as we kind of make this interruption model richer. And I think probably realistically, as much time as we spend on this, it's not going to get as rich as the one on the actual ZIO because this is a really complex area. This is kind of why you use the actual libraries. But I think already it's kind of good to kind of get a sense of how this stuff works. Okay, let me just do a brief check-in on if anyone has any questions here.
Nothing in the Discord.
Okay, someone had a debugging suggestion, but I think we got that. Okay, so this is great, but let's think about limitations of this. Does anyone maybe want to try to like type in the Discord like some things that are not where we would want them to be with this yet? Okay, well, let me have one for us that I think will highlight kind of interesting thing with this whole implementation. So you can see this worked really nicely here, where we had this like ZIO.never thing. Or in general, this kind of will work well when we have an asynchronous thing that is just we're waiting for some third-party API to call us back, and then we decide as we're doing it that we don't want to keep doing that anymore. But let's say, so let me see if we've got this operator. I don't think we have it quite yet, but we can make it. So let me implement another operator that's just called forever. And this is going to return a ZIO nothing. And this is just going to say run ourselves and then call this again. So we're going to run ourselves again, and then we're just going to call this again. And we're going to do this forever. And I think I need to actually make this by name so that doesn't blow up. But what that will let me do is do something like, okay. Example.
Did I excuse me? No. Okay, cool.
And so let's say I do this dots forever.interrupt. Is this actually printing dots? Or?
Oh, let me see. That's odd. I wonder if is something wrong with print, because that happened in the previous one as well. That just nothing. Should I just do print line? Why is print broken? I'm just going to do debug because we've used debug before. I don't know why. Nothing's
Yeah,
printing.
Yeah.
Let's try ZIO. That works.
Okay.
Can we define our own print? Why? That's so
very
weird.
strange. I mean, part of this maybe, it probably means we have a little bug with something else we're doing, but that
What if we just do one dot? Obviously,
yeah.
will
Let's
not be.
start with that and see if we've got something. Let me make sure we've saved here too.
Yeah, it's very interesting.
strange.
And there's no problem with the fork comprehension because, yeah, I mean, basically it's just doing two things, starting another message. Is it because of the fork? What happens if we just do that? Like, is there something wrong with our fork comprehension?
Okay, all right, let's take a look. We're going
And then
all sorts of fun debugging here.
That's okay, so that does, and if we fork it, I'm guessing now nothing's going to happen, I would imagine. Otherwise, I'm deeply confused because it's literally the same exact thing as the dot.
No, that works.
Right? What? So if I do a dot and fork it, then it's going to work?
All right, let me see. Yeah,
what?
That's fine.
How is it pulling it into a method breaking it? What the? Okay, I don't understand. Let's just do it inline then. Dots forever dot fork.
Okay, let's see if this works for us.
Fiber, sorry. There we go.
All right.
What?
All right. Well, anyway, so we'll come back to that.
Yeah, very weird.
Anyway, what you're saying here is this isn't stopping. And if you think about this I guess makes sense on a couple levels. Let me first I think I probably need to blow this whole thing up. Okay, there we go. So why was that not stopping? Well, the basic answer is in this whole model, like think about this fiber as this mini actor. So we're only processing messages from the inbox when the fiber goes back to the inbox, which is either if the fiber is not running or when the fiber starts or stops running. So if the fiber is just running forever, so essentially what we have is this run loop is just running over and over again. The fiber is never going back to the inbox to check if there's more stuff in the inbox. And so what we need to introduce here is essentially some idea of yielding, that after the fiber has done a certain number of operations, even if it's got more operations to do in the run loop, it's just going to stop doing those operations and it's going to check for more stuff in the inbox. Does that make sense?
Yeah, I think so. I mean, maybe we're getting this getting to this as well, but it seems like maybe I'm not sure what the actual ZIO does, but we could also have like a flag saying interrupted and check that, right? Either you're decrementing a yield counts or just check every loop. Or have we been interrupted in the background? Would that be a? Oh no, because we haven't. This is happening sequentially, right? So it's not
right. This is kind of the flip side of our nano actor design. Is no one, like, even if we check a variable for whether we're interrupted here, no one else can set that variable because that's the whole point of our design. Is we're the only ones who set this variable. So we need to take a break ourselves to check these messages.
Is that a trade-off? Is that something that exists in real ZIO, or are there other, is there one more atomic Boolean that we have and we allow that case? Or I'm guessing not.
No, it works exactly that way. There's a certain number of operations, and then you yield, and then you check for interruption. So it's exactly the same.
Cool. I'm guessing in reality that all happens so quickly, everything in the run loop, that it doesn't, like, you don't need to interrupt this nanosecond. You can wait for a couple more operations. But anyhow.
Exactly. So what we can do here is we can keep track of some other variable here. A lot of times this would be called like the op count. And this will be 0. And then, yeah, exactly. We'll have some global variable that we can pick whatever number we want. And then the first thing we're going to do in the loop here is we're going to say op count plus equals 1. So we're going to increment the op count.
Yeah.
And then we're going to say, this is not quite right, but I mean, GitHub Copilot is making a valiant effort here. But so basically, if we do get to this op count, then I don't think we actually, we're probably just going to throw it out of here. So we probably don't need to zero it out because there's only been a local reference here. Actually, I think we'll just leave that. But so here we need to think about how we are going to do this idea of we kind of want to yield back control here. And so we can look a little bit at what we did with this like async node here. And so what we did here was we stopped the run loop, we set this equal to null, and then we offered to the inbox a message that was just going to resume with this ZIO. So let's try that. So let's say that we're going to and maybe I'll just say
do we want to do the actual current ZIO, right? Not val current ZIO? Or
yes, sorry. Okay. Let me see, do I have terminal working again after I blew everything up? Not yet.
Great. And this is I mean, we could make some method that like just pulled off one message, but I guess by offering to the inbox, we're going to process all the messages that came in before this particular resume, right? So a little more fair.
Right, and we're trying to, well, and partly I think we're just trying to retain simplicity here of this way, the logic for what we do when we process things and offer things, it's all kind of the same. Versus having to do any special casing here. Though, as folks have seen, it's also easy to introduce bugs here, so we may have fun stuff here. Okay, so we're going to do the stop thing forever. We're going to wait 3 seconds, and we're going to try to interrupt this thing. And so our expectation would be now that eventually we're going to hit this. I think we set it to 300. I think it's actually like 1,000. But we can, at that point, we're going to yield back, then we're going to process the interrupt message, and then we're going to go from there. So let's try running this. Oops. Okay. So we got lots of dots.
Yay.
And look at that.
Good.
So now we're starting to get this a little bit closer to real world type situations because I mean, definitely the async one is a pretty common case of like a lot of times when you're waiting, it's because you're waiting for some third-party API. But sometimes you also just have some ZIO computation that's just going through a bunch of different steps and eventually you want to stop it. And so now we've got that functionality working. Any questions on any of this?
Let me check the Discord. So we also had a couple of, I know it's hard asking questions to the Discord because I think with the streaming delay and then the thinking plus typing, it takes a little bit of a gap, but we got a couple of answers. It's like, we're missing finalizers. And I think that is true, but I think we're gonna get to that later. That's definitely something that's missing in general, but we will wait for the run loop to finish or be waiting for an async result. Yeah, so I think that's exactly what basically the problem was, right? The run loop was never going to finish. But yeah, I mean, that seems clear to me. It's definitely I think I've said this every time, but like this very nice little nano actor abstraction is great because especially as now we're really piling on more and more features. I just remember with the ZIO 1 version, each new feature had that same amount of like, we kept having to think about the weird, nasty concurrency edge cases. And now we sort of dealt with that. And it's just, everything happens one after the other. And it's easy. And we have variables. No compare and set.
Yeah, exactly.
So yeah, that looks great. Well, what would the next steps be? Maybe we could pre-plan some further parts.
Yeah, exactly. So I think the next concept from here is, maybe we go back to our little to-do list. So we generalized to include cause. I don't know if I know how to make these, like I can copy and paste your fancy check marks. I don't know if I know how to type them myself.
And we did very useful shortcut.
And we did support interrupting a workflow and getting its results. So I think the next thing we have here is this concept of interruptible masks or regions. And so basically the next step would be introducing essentially a flag into the fiber here that says whether it's interruptible or not. And then we would expose some operators that would let us change that flag of make it interruptible or not interruptible. And some operators for working with that. And then we would need to update some of our logic for kind of how we handle getting interruption when we're in a region where we're not interruptible. And like, what if we were uninterruptible, but now we become interruptible and we already have an interruption, and basically build in the logic for that. And that would give us the building blocks to implement like finalizers and resource safety in the presence of interruption. But yeah, I think we're at about an hour here, so this may be a good stopping point, and maybe that can be the project for next time.
Yeah, that sounds good to me. I think it's definitely, nice for the videos to have them a little more digestible at an hour. And one topic. Not
an hour and a half.
Yeah,
I think that's a good plan.
I recently found also a plugin, or it's like a free App Store extension that you can get up to as many times speed as you want on YouTube. So I've been trying to watch some 3 times speed videos, and it really, you try that, you can get through all the Zymposiums really quickly, and but it's exciting. But yeah, that was super fun. Thanks, Adam. And I'm guessing you went over at the beginning that little, because I know last time we were stuck in a little debug.
Yeah, we went over that one thing. Yeah.
Awesome. That one little thing. All right, great. All right, well,
cool.
Till next time.
Yeah, thanks everyone, and I'll push this code up.
Awesome. Thanks, Adam. Bye, everybody.
All right, bye.